Let's look again at the data for under 5 mortality and GNP for the 75 countries we've been working with. It's already been said that the log of GNP has a relatively linear relationship with under 5 mortality. But there are other ways in which to try to fit a regression equation to a nonlinear relationship. Let's go back and recreate the graph that we were working with before. Scatter chart. When I finish this, I get this graph, which is basically a nonlinear relationship. One way to try to fit a regression equation to a nonlinear relationship, particularly if it's a curve that makes only one change of direction, as the curve through this line would, is to use a second-degree equation. A second-degree equation is a regression equation that includes the value of the independent variable, in this case GNP, and the square of the independent variable. These two variables taken together will create what is called a second-degree curve, or a curve that has one change of direction. In order to look at that, let's move this out of the way, and we'll insert a column right here, and we'll make this GNP hat 2. And in this column, I will create the square of GNP. So that's the first value. When I do a Control-Shift down arrow, I get the square of GNP for all of the variables. Now let's see what happens if I use GNP and GNP squared to create a new regression equation. I'll go to Tools, Data Analysis, Regression, OK. The dependent variable is under 5 mortality. The independent variable set now is GNP and GNP squared. There are labels in the first row, and the output will go in F1. When I click OK, I get this result. Now I'm accounting for 39% of the variance in under 5 mortality, which is substantially better than I accounted for with GNP as the predictor alone. There's a coefficient for GNP and a coefficient for GNP squared. If we look at the p-value for each of these, they are both significant, well beyond the 0.05 level. And what does the result of this look like if we graph it? Here we're going to have U5 mort hat, and now predicted value of under 5 mortality will be equal to the coefficient for GNP fixed with an F4 times GNP plus the coefficient of GNP squared fixed with an F4 plus GNP squared plus the intercept, again fixed with an F4. These are the predicted values for under 5 mortality. Let's look at the graph again with under 5 mortality, GNP, and the predicted values of under 5 mortality. If I add the predicted values to the graph now changes. You can see the points that represent the predicted values, and this is a curved line. That's the effect of a second-degree curve. The prediction may not be too bad for these points. It's quite bad for these 2 points where the prediction is under 5 mortality at a very low level, minus approximately 80, which is totally unreasonable. Here's also a minus prediction, and here is a positive prediction. And if we had dollars going further out this way, the line would continue up in this manner. So while we can use a second degree equation, that is, in this case, GNP and GNP squared, to predict under 5 mortality, and while our prediction at 39% is better than the straight line prediction we made with GNP alone, the curved line we've created still doesn't fit the data very well.